Okay, so we were discussing this thing, hydrostatic paradox. What is your understanding of this? Did you read this? You didn't? Okay. So this particular picture that you're seeing here, this one is an explanation of hydrostatic paradox. But it says that if you say fill a fluid, liquid, in tubes connected like this, and tubes are of different shape, right?
Yes, sir.
What do you expect? To what height the fluid will rise in each of the portion?
Same height.
Huh?
Same height.
Why will you expect it to rise to the same height? There should be a reason, right?
Yes.
So what is the reason that you said, okay, in each of the section, it should rise to the same height? It is visible that way, but what is the reason? Can it rise to different heights also? You see, shapes are different, right? So this is a longitudinal cylinder, this is conic cylinder, and this is inverted cone cylinder, right?
Yes, sir.
Inverted cone, and cylinder. So why is it rising to the same level? Because the volume here is different from volume, total amount, right?
Yes, sir.
But how is it going up to the same level? This is proven actually based on the experiment that we have seen earlier, Pascal's law. And in Pascal's law, what we have seen is at a particular height or depth, the pressure is constant, right? The pressure variation happens with depth, but at a certain depth, the pressure doesn't differ. I mean, pressure remains the same, right?
Yes, sir.
And the same thing is applicable here. When you found this gauge pressure, when you were trying to calculate the gauge pressure, P2 minus P1 is equal to rho g h. Rho and g are constant. Only thing that is variable here is h, and h is what? Depth or height, right?
Yes,
It
sir.
has no relationship with the cross-section area or shape. Only the column or height of the liquid, height of the fluid, that is important. And then that is why whatever may be the shape, the liquid or fluid will rise to the same level. Okay, this is called hydrostatic paradox. On filling with water, the level in the three vessels is the same, though they hold different amounts of water. This is so because water at the bottom has the same pressure. Water at the bottom has the same pressure below each section of the vessel, right? Water at the bottom. Here it is common, right? So it has to have the same pressure, uniform. It cannot have some pressure here, some pressure, some different pressure here, another measurement of pressure here. So it has to have the same height of water above it, because above the water you have open air, right? And in
Yes, sir.
open air, the atmospheric pressure is not changing, it's not different. So additional pressure at this point of the water will be the height of the water, rho g h, rho g h, rho g h here. Then only the pressure remains constant. Okay, let's do this problem. What is the pressure on a swimmer 10 meter below the surface of a lake? Would you like to try this question on your own first?
Yeah.
Try it. Okay, so what we got here was the pressure 10 meter below. So the 10 meter below pressure will be atmospheric pressure, which is at the surface of the lake, and then the pressure caused by the column of the water, which is 10 meter high. So total pressure will be PA, atmospheric pressure, plus rho GH. Rho is what? Density of water, which is 1000 kg per meter cube. Height is 10 meter, and assume G is 10 meter per second square. So this comes to 1000 into 10 into 10, which is 10 to the power 5. And atmospheric pressure is anyway known as 1.01 into 10 to the power 5 Pascal. So total is 2.01 into 10 to the power 5 Pascal. So approximately 2 atmosphere. 1 atmosphere is 1.1 into 10 to the power 5 Pascal is 1 atmosphere. Okay. The atmospheric pressure value is called 1 atmosphere. So this is a 100% increase in pressure. So you go 10 meter deep and your pressure increases almost by 100%. It doubles. If you go further 10 meter deep, it will triple, right? Right? That is how it is happening. Okay, so that takes me to a question. If I go up in the air by 10 meter, will atmospheric pressure reduce by 1 atmosphere? I'm going deeper in the water, and by going just deep, 10 meter deep, the atmospheric pressure is doubling, right? If I go up in the air, say up in the air in the sense, if I go uphill, 10 meter up, okay, will atmospheric pressure change in the same proportion?
Yes.
It will?
Yes, sir.
Okay. How will it change to the same proportion? What will be rho in that case? If what is the rho value of rho that I will consider? Why did I take 1000 kg per meter cube as the density? This density is of the water. The fluid here is water.
Yes, sir.
Now, if I'm going uphill, am I going up in the water? What is the fluid that is causing atmospheric pressure? What is the fluid that is causing atmospheric pressure? Just think about it. It is air, isn't it?
Yeah, sir. Yes, sir.
Atmosphere contains air, gases,
Yes, sir.
right? So that is causing the atmospheric pressure. Now, if I go up in the air, say uphill, right? Or if I go to, say, 10th floor of a tower, right? It is 100 feet above. So 100 feet is approximately 10 meter.
Yes.
No, it is more than that. 30 meters. 30 meters, right? But rho is different there. Rho, the density of the fluid which is causing that pressure, will not have this density. The air will never have this density. Water is much denser than air, correct?
Yes.
So G is of course 10 meter per second square. Height, of course, I may go up 10 meter, but rho has a very, very low value compared to that of water. So if I go up in the air, pressure will reduce, pressure will change because H is negative, minus H, minus 10. So rho GH, well, pressure will reduce by some value, but because rho is very less, actually 1 kg per meter cube maybe, I don't remember the density of air, but it is definitely not 1000. So the reduction that will happen will not be in this proportion. Instead of, say, liquid water, if you go in, say, a column of mercury, that is much thicker, means higher density. So if you go deeper, 10 meter deep in mercury, that the pressure may triple. It depends, right? So how will I know what is my density? I must know the fluid density before calculating the change in liquid pressure, right? Fluid pressure. Here we have the densities. Air has the density of 1.29 kg per meter cube, right? And water has 1 into 10 to the power 3. If it is 1000, this is 1.29. That is the difference, right? So to have a reduction of 1 atmosphere, I will have to go 1000 meter, approximately 1000 meter above. Then I will have a reduction of 1 atmosphere. Okay, that is what is important to understand. Mercury has 13.6, so it is 13 times thicker than water. That means if you go 1 meter deep in mercury, you will have a change of atmospheric change of pressure by 1 atmosphere. You see that? So this is important. You need to understand what is the fluid that I am considering for calculating the change in pressure. Okay, what is gauge pressure? What is gauge pressure? We learned that term in our previous class. What is gauge pressure?
So like the excess of pressure.
Yes. The difference in pressure that we generally measure, excess of pressure. The excess of pressure P minus PA at depth H is called a gauge pressure at that point. So excess from the atmospheric pressure. The difference, additional pressure than the atmospheric pressure, is called gauge pressure. All our equipments that we use to measure the pressure, most of them will be measuring the gauge pressure. So we may have to add the atmospheric pressure to find the absolute pressure, right? Okay, so somebody created a device to calculate the pressure, fluid pressure. And the person who created a device was named as this Evangelista Torricelli. Why I am bringing this name? Because very soon you will see there is a unit of pressure that is in practice is called Torricelli. So you'll have to remember this because Torricelli will come again. Okay, so at sea level it is the atmospheric pressure is 1.013 into 10 to the power 5 Pascal, or which is called 1 atmosphere. Torricelli created a device, a long glass tube, where it closed from one end. It's like a small glass tube where you can fill some liquid, and what liquid was filled? Mercury. And that liquid was inverted into a beaker or another container of mercury. Once it is inverted, what happens? Some fluid, some mercury will go down in the larger pool, and then it will become a stationary, it will reach an equilibrium state, and the height that is left in that tube, the height of Mercury, is equal to the atmospheric pressure in the outer side. You have seen this apparatus, you have seen this in your previous class as well. So here is the apparatus, this one. You have seen this in class 8, I believe, where you were learning about pressure. Okay, so this is the tube which contains mercury, and this is another larger container which contains mercury. Okay, you fill it completely and invert it, dip it, inverted dip into this one. So what happens? Some mercury will come out of this, and how much will come out? That will become equivalent to the, so of course once the liquid fluid comes out of this tube, it will change the level of fluid here in this larger container, right? Because
Yes, sir.
it's coming out and it is just getting stored again in this, so the level will rise. Now this level will rise to an extent where the atmospheric pressure outside this, on this surface, and pressure of this column of fluid has to be equal, right? Then only it will reach a equilibrium state,
Yes, sir.
right? So
Yes, sir.
this is a very easy combination, a very easy arrangement to measure the atmospheric pressure at any point, any place, because this is the column of liquid. If you, what is here? What is here? It is some pressure, okay, but this is negligible because here you will have only vapor of mercury, this vacuum, the empty space. If you break it, then this point will also experience, the point P here will also experience a atmospheric pressure. So what will happen? It will completely come out of this and reach an equilibrium, because this tube or this big container both will experience the same pressure, because those both are open to air, open to atmosphere. But this one is not open right now because this is closed from this end. Now when this is closed from one end, whatever column of mercury that is left, that has to balance out the atmospheric on the other side, atmospheric pressure on the other side, outside, right? So
Yes,
if
sir.
you measure the height of this, which is say h, multiply it with mercury's density and acceleration due to gravity, you will get a measurement, right, in Pascal, that will be equivalent to external atmospheric pressure. This is called, this apparatus is called the Mercury Barometer, and it was created by Torricelli. Okay,
Yes,
to respect him again, Torricelli is also used, or TORR. This is the unit that is used to state the pressure in terms of height of the mercury. It can be say mm of Hg, mm of Hg, or cm of Hg, millimeter of mercury, or centimeter of mercury. The height of the column of mercury is very commonly used as uh, pressure. You have seen this kind of apparatus in hospitals, basically, that is used to measure the blood pressure. So have you seen that blood pressure where the doctor will do a little bit of pumping, and there will be a rise or fall of mercury in a tube, right?
yes,
Have you observed that? Okay. So there, the measurements will come like, what is the normal um, blood pressure of human being? What is the normal value that you might have seen? Okay, sometimes somebody says, I have high blood pressure or low blood pressure. So what is the normal value? Just numbers. You might have heard of some numbers.
Performance.
Okay, so it is, there are two values that will always be said, high and low. High, which is called systolic, and the measurement of that is generally 120. And
Yeah.
diastolic, down lower value, is called 80, 120 by 80. That's common. In common conversation, you will hear this term, 120 by 80.
Yes.
Now, what is 120 by 80? I told you in physics, in science, there is no value without unit. 120 by 80, what is that? Is it 120 kilometer by 80 kilometer? I mean, quantity could be anything. Unless I qualify it with a unit, it has no sense. So, what is the unit associated with this blood pressure values? That is mm of Hg. If you see the prescription written by doctors, they will not just write 120 by 80. They will also write 120 by 80 mm of Hg. Hg is the unit, is the symbol of mercury, right?
Yes.
Hg is the symbol of mercury as element. So mm of Hg means millimeter height, 120 millimeter of Hg. That is actually indicative of this apparatus, Mercury Barometer, which says, okay, when I measured the higher part or systolic measurement, I took the systolic blood pressure, the measure was of this equivalent to this height of mercury column was 120 millimeter. Okay, and when I measured the diastolic one, the lower one, it was 80 millimeter. Okay, now how that relates to blood pressure, that's a different story. I don't know, and I don't want you to get into that medical dissection of that. But from the pressure point of view, that's a liquid's pressure, right? That is being measured. So 120 mm by 80 mm is the common measurement that you have seen, right? So that is a common terminology that is used, and there 1 mm is called a torr or torricelli. So instead of 120 mm of Hg, it can, somebody can write 120 by 80 torr. That itself indicates 1 mm height. 1 torricelli is equal to 1 mm height. Okay.
Yes.
Okay. So 1 torricelli is equivalent to 133 Pascal. And now what is Pascal?
The unit of pressure.
That's the measurement of pressure. Rho
Yes.
G, SI unit of pressure. Correct?
Yes.
So 1 torricelli is 133 Pascal. There is another unit that you should remember, which is very common in medicine and physiology, again medicine related or medical science, is called bar and millibar. Okay, bar and millibar. And 1 bar is equal to 10 to the 10 to the power 5 Pascal. So 1 atmosphere is 1.01 into 10 to the power 5 Pascal, right?
Yes.
Okay. So 1 bar is approximately equal to 1 atmosphere. So you see the pressure has many common units. Pascal is official SI unit. Then you have mm of Hg. Then you have torricelli. Then you have bar. And I had asked you to ask some question to your papa. Did you?
No, sir, I didn't have.
Okay, I will tell you. But you should ask, right? You should be more inquisitive.
Yes.
You have to be. Then only you will learn new things which are not there in the book. Okay, so I had asked you, what is the unit of tire pressure? The air pressure that you uh, see in tires, vehicles' tires. What is the unit, common unit? Somebody will say, if you go to petrol pump where you get air pressure, air filled, they will ask you, how much? 30, 31, 33? It depends. And on many buses also you will see something written this much quantity, 120 or like that, near their wheel. But there is a unit again, because physical quantities has no existence without a unit, no meaning without a unit. So the unit that is used there is PSI. PSI. And that is another unit. You know, pressure is what? Weight per unit area, or weight is equivalent to force, right?
Right.
Force per unit area is pressure. Okay?
Yes.
And weight is having different units. So it will be kg, Newton meter, Newton, or pound. FPS system has pound. You have stayed in America, so you know what FPS is. Pound is a common measurement of weight. 1 pound is equal to approximately 450 gram, right?
Yes, sir.
Pound, ounce, gallon. You might have seen all that in your stay in America when you went to Walmart or some other place like Costco. Huh?
Yes.
So you have seen those measurements, pounds and gallons and all that. So pound is the measurement of weight, and inches, feet are the measurement, feet, mile. These are the measurements of length. Okay, so area will have unit like square inch, square feet, square mile, square hectare, square acre. Rather, hectare and acres are the general unit of area. There is no need of squaring it. Okay, so square inch, square feet, and square mile could be the area of the unit of area. PSI, say 30 PSI that you see in as suggested value of tire pressure in your particular vehicle, that indicates 30 pounds per square inch. PSI stands for pounds per square inch, another unit. So pressure has many units, and that leads to confusion. And again, a lot of questions where you will be given values in one unit, you will have to find it in another unit. Something, say pressure is given, area is given, you have to get the weight or force. You need to know these relationships, you need to know these conversions. So okay, so in your notes you should write, first of all, what is the value of basic measurements in each unit. Say 1 torricelli is equal to 1 mm of Hg, and then again do a relationship also. So 133 Pascal. Now what is Pascal? 1 Pascal is 1 Newton per meter square. Okay, so from that you can get how much pound per square inch, PSI. So 1 Pascal into PSI is how much? 1 torricelli in Pascal is how much? 1 bar to Pascal is how much? All those units from one to another are related but have different quantitative values. So you need to know the conversion rules for all units of pressure. Okay, so
Yes.
that particular device that you see, that you saw, a Mercury Barometer, was created by Torricelli. There is another device to measure pressure is this open tube manometer. Now, manometer is another term which is used for those devices which are used to measure pressure or pressure difference. Manometer. It's a common general knowledge question. Very common. What is the device, name of the device that is used to measure pressure? So one is manometer, another is barometer. Barometer is generally used to measure the atmospheric pressure. Barometer. Manometer is generally used, again, you can measure the atmospheric pressure as well as the difference in pressure at certain point. So gauge pressure. Manometer is used as gauge pressure measurement tool. Okay, so here it is like this. You have a tube open from both ends. So when it is open from both ends, what you will see is normally the fluid will have same height on both ends, right?
Yes.
Now what you do, you connect one end to a device where you want to measure the pressure. At this point, what is the pressure? Say fluid is passing through, some air is passing through. You connect this end of the manometer to that, say, tube, right? So it will put up some pressure here, and that will be equal to the pressure that is applicable at this point, right? So if that pressure, if it is more, it will push the liquid on the other side, right?
Yes.
And it will push down until it reaches an equilibrium state again. Okay, at this point, say it pushed the liquid in the manometer to this point, say A. So at this point the pressure has to be equal to the pressure at this point, say B, at the same height on the other end of the tube, other, because it is like a U tube, the pressure here has to be equal to the pressure here. Now what is the pressure here? B. This is equal to PA, the atmospheric pressure, because this end of the manometer is open to air. So this is experiencing two pressures. Pressure at point B is equal to PA plus the pressure caused by this column of liquid. And what is this column? The extra height above B, right? So you know the pressure at point P will be equal to PA plus rho GH. So this will be, rho will be the density of this liquid. It may be water, it may be mercury. Depending on the liquid, you will have to use the density of that to find what is that additional pressure. So PA plus this pressure is equal to the pressure at point B, and so that is the pressure on the other end also at the same height, point A. And what is the pressure here? Actually, the pressure coming out of this tube. So this is how you indirectly measure the pressure on this end. Okay. So
Yes.
manometer is used to measure the pressure of any liquid, any fluid, while barometer is generally used to measure the atmospheric pressure. So that is a technical difference that you should remember between these two devices. But ultimately, both are used to measure the pressure. Okay.
Yes, sir.
Now this whole section here is describing the same uh, phenomena that are how this operates. So you can read this and understand. Let's try to solve this problem. The density of the atmosphere at sea level is 1.29 kg per meter cube. Okay, density of atmosphere at sea level. Atmosphere means air, not water. Assume that it does not change with altitude. Altitude means height. Then how high would the atmosphere extend? Okay, so what is being asked here is, you know The density of atmosphere is 1.29 kg per meter cube. Now you tell me, what is the height of the air that causes this much pressure? So you know what is the atmospheric pressure at sea level. You know that. 1 atmosphere, and that is equal to 1.01 into 10 to the power 5 Pascal, right?
Yes, sir.
What you have been given is rho or density of the air. G, you already know, 9.8 meter per second square, or you can assume 10 meter per second square. What you don't know is the height of the air column that is creating that much of pressure, when atmospheric pressure. Okay, so simple, rho, G, and H is equal to the known value of atmospheric pressure. Known value of this is measured using, say, apparatus like barometer. Okay, and from here you can do some calculation and you can find that H comes to approximately 8,000 meter or 8 kilometer. Okay,
Yes, sir.
but what is important here is the density of atmosphere is assumed to be constant. It is not changing with altitude. But reality is air gets rarer. The density reduces as you go up. Density will continuously change. Density is highest, density of air is highest at the bottom, and it changes. And because it decreases over altitude, the height of air that causes this pressure, atmospheric pressure, is not just 8 kilometer, it can go up to hundreds of kilometers. So our atmosphere, the height of the atmosphere is not just 8 kilometer, it is much more, 100 kilometer. In some books, it will be mentioned as 300 kilometers. In some other book, it will be mentioned as 500 kilometers, right? So it depends. Only one of those will be correct, right? So there are different justifications for those measurements, but if you have to assume that density is constant, you will get only this much value. And again, if this assumed density is something else, well, if you assume, okay, it's in summer, so in summer density will be lesser, in winter some density of air will be more, so again you will get a different value for height. Okay,
Yes, sir.
in terms of of Hg, sea level atmospheric pressure is termed as 760 of Hg. So 1.01 into 10 to the power 5 Pascal is approximately equal to 760 of Hg, or 760 Torricelli, right? That's an assumption. But again, it varies because my assumption is not accurate. Okay, so what I expect you to do now is attempt few more related problems and then have a reading of the remaining sections. Hydraulic machine, for example, you might not have studied machines in your previous classes. I don't know if, I think CBSE classes did not include anything on machines, but ICSC has machines, simple machines, as a chapter in class 10, and in class 11 you have a concept of pulleys, right? Pulleys, and you have, right, you have that chapter,
Police
pulleys,
did.
ropes and pulleys, right?
No, in 10th grade we did have.
In 10th grade itself it was. So you know what is mechanical advantage, and you VR and MA, right? Velocity ratio and mechanical advantage. Those kind of terms will come here in hydraulic machines because it is technically a machine. So you will find something interesting here. So read about that and how it operates. There will be some relationships like L1A1 is equal to L2A2, some numericals on that. And then we will learn about something new, which is related to turbulence and Bernoulli's principle and surface tension at a later stage, right? So little more terms will come, venturimeter. Okay, interesting things will come going forward. Viscosity and Stokes law, Reynolds number. Lot of terms are coming here, which are related to fluid, and finally surface tension will come. So there are so many concepts that will come in this chapter. I strongly recommend you to have a reading of this chapter, and while reading, do the reverse reading. Start from back.
Okay, sir.